All right, welcome to this explainer. Today we're demystifying how internet routing and subnetting math actually work. And the best part, we are going to entirely bypass the tedious weeds of binary translation and focus purely on practical mastery. If you've ever stared at an IP address and wondered how it dynamically connects your specific device to the rest of the world, well, you are in the exact right place. Let's just jump right in.
So to kick things off, let's ask a super fundamental question. How does a single packet of data know exactly where to go on an internet packed with literally billions of connected devices worldwide? I mean, without addresses, a packet of data would just be completely lost in the noise. Every single device on the internet needs a unique numerical label, an IP address, just like every house on a street has a specific door number. That IP address acts as the delivery address. It tells the network, hey, this data belongs to this specific device on this specific network, and it just hops from router to router until it finally reaches you.
Here is our game plan for today. 1. The global delivery problem. 2. Drawing your network boundaries. 3. Mastering the CIDR shorthand. 4. Subnetting calculations made easy. And finally, number 5, the end-to-end journey.
All right, part 1, the global delivery problem.
Okay, let's dive into this. An IP address is exactly like a global postal address. It uses a network part for the city and a host part for the specific house door. Now, the whole internet was built on a format called IPv4. It uses 32 bits, which gives us those familiar 4 numbers separated by dots. And this underlying IPv4 structure provided roughly 4.3 billion unique addresses. Back in 1983, that seemed like plenty, right? But literally nobody anticipated that billions of people would each own multiple internet-connected devices. This quickly led to a massive exhaustion crisis as the internet just exploded. The city simply grew way too fast, and we ran out of new building codes to hand out to everyone. So to preserve that dwindling space, we came up with a pretty brilliant workaround, separating the globe from the internal office building, using public and private IPs. Private IPs were created purely for internal home and office use. These are addresses like your standard 192.168 network at home. They are not directly reachable from the public internet, which honestly adds a fantastic layer of natural security and isolation. Instead, thousands of internal devices can share just one globally unique public IP, and this happens through a process called Network Address Translation, or NAT. Think of it like a massive company building. The private IPs are the internal office extensions, while the public IP is the one main external phone number the outside world actually calls. Your local router acts as the receptionist, bridging those two worlds.
Which brings us to part 2, drawing your network boundaries.
Now that we understand the addresses themselves, we face a whole new problem. Having thousands of devices on one flat internal network creates chaotic noise. Every single broadcast message reaches every single device, which just wastes precious bandwidth. Plus, you have absolutely zero logical isolation between, say, your HR computers and your engineering servers. Subnetting solves this by creating isolated segments. It basically divides a larger IP network into smaller, logically separate subnetworks. This controls exactly which devices can communicate directly without needing a router, cutting down the noise, organizing IP allocation, and enforcing strict security.
I love this analogy. Think of subnetting like dividing a large apartment complex into separate wings, each with its own locked door. Residents within the same wing can walk freely and talk to each other without any barriers at all. But to visit someone in another wing, you have to go all the way down through the security desk in the main lobby. In our networks, that security desk is exactly what a network router does. It checks if you're actually allowed to cross into that other subnet before letting your data pass through. But you might be wondering, how does a device actually know where its wing ends and another begins? Well, that's where the subnet mask comes in. An IP address by itself is actually pretty meaningless because it doesn't tell you where the network ends and the device begins. The subnet mask acts like a 32-bit highlighter applied right over a postal address. The parts that are highlighted in the mask represent the network portion, telling routers how to get to the right neighborhood. The unhighlighted parts represent the host portion, telling the local network which exact door to knock on. You literally cannot have a functioning IP address without its accompanying subnet mask.
Okay, moving right along to part 3, mastering the CIDR shorthand. So how does this build into our main focus of mastering these boundaries? Well, writing out long subnet masks like 255.255.255.0 every single time is painful and super inefficient. So modern networks use an incredibly efficient shorthand called CIDR, or classless interdomain routing. CIDR completely removes the old rigid network classes that used to waste millions of IP addresses. Instead, it uses a simple slash number to tell you exactly how tightly the boundary is drawn around a network. That slash number just tells you exactly how many bits of the 32-bit IP address are permanently locked in as the network portion. Now, check out the relationship here between the CIDR prefix and the usable network size. You might intuitively think a bigger number means a bigger network, right? Actually, scratch that. It's the exact opposite. A larger prefix number actually means a smaller network. Why? Because more bits are locked to the network portion, leaving way fewer bits available for the devices, or hosts. For example, a /24 leaves 8 bits for hosts, giving you 256 addresses. But a /30 locks down 30 bits, leaving only 2 bits for hosts, resulting in just 4 total addresses. Notice too that your usable hosts are always 2 less than the total. That's because the first address is strictly reserved to identify the network itself, and the last address is reserved for broadcasting messages to everyone on that specific subnet.
All right, part 4, subnetting calculations made easy.
I know a lot of people get totally intimidated by subnetting because they think they have to sit there writing out 32 bits of tedious binary every single time. We are not doing that. We are going to use the block size method, which is basically a massive cheat code. Given an IP and a CIDR slash, you just follow these 4 logical steps. First, identify your host bits by subtracting the prefix from 32. Second, calculate your total addresses by taking 2 to the power of those host bits. Third, subtract 2 for your usable hosts, remembering our network and broadcast reservations from a second ago. And finally, determine your block size to step through the network and find your exact boundaries.
Let's actually see this in action, because seeing is believing here. Say you're given the IP 192.168.10.50 with a CIDR of /26. Step 1, 32 minus 26 leaves us 6 host bits. Step 2, 2 to the power of 6 gives us 64 total addresses. That 64 is our block size. So we divide our 256 possible addresses in that final octet into blocks of 64, 0 to 63, 64 to 127, and so on. Now, where does our IP of .50 fall? It falls right into that very first block of 0 to 63. This instantly tells us that .0 is our network address, .63 is the broadcast address at the very end of the block, and .50 is a perfectly valid usable host, right in the middle. Boom! We've mastered our subnet boundaries with 0 binary translation required.
And finally, part 5, the end-to-end journey.
Let's bring all these concepts together and imagine tracing a single real-world packet from a private workstation out to a public Google server and back. In millisecond 1, your private device at 10.0.1.25 checks its CIDR mask. It realizes the destination Google IP isn't in its local /24 subnet. So in millisecond 5, it hands the packet over to the security desk, the default gateway router. At millisecond 10, the router stamps its public IP onto the packet via NAT so it can actually survive out on the open internet. By millisecond 50, that packet has traversed global routing tables to reach Google's network. And by millisecond 100, the reply comes back, hits your router, reverses the NAT translation, and gets delivered right back to your exact private workstation. The whole shebang in a fraction of a second.
The big takeaway here is that every single concept we just talked about plays a very specific part in that microsecond journey. The IP addressing identifies the unique source and destination at every single step. The public versus private architecture isolates our internal traffic from the open web, keeping us secure. The CIDR notation triggers that critical initial routing decision of whether the traffic is local or remote. NAT handles the complex translation across the public-private boundary, and subnetting enforces the underlying control and traffic isolation that keeps the whole system stable and secure.
So, we've nailed down how to draw these boundaries and calculate subnets in IPv4. But as we eventually migrate to the massive 128-bit IPv6 architecture, where there are 340 undecillion addresses, which is literally enough to give a unique IP to every single grain of sand on Earth, we have to ask, what happens to our carefully learned network boundaries next? How will our CIDR math evolve when we never, ever have to worry about running out of addresses again? That is a massive shift in how we think about the internet, and a fascinating challenge as our networks continue to grow. Thanks for joining me on this explainer. Keep exploring, keep mastering your networks, and I'll catch you next time.